Hello, students. Welcome to Math 106. I'm going to start with section 8.1. And before we do this fantastic puzzle that is listed at the beginning of chapter 8. Now, this chapter is about algebraic thinking. We will be covering things that you may think are more algebra, but I'm going to be doing my best to show you how they connect to elementary school classrooms. It is not just about manipulating with variables. Students at all levels need to understand how these work, and that'll be kind of our goal for this term. So let's see. Okay, I'm going to, for example, let me just give you an example here. So this problem right here, this is a pretty fun one. So when you look at this problem, you see, you see what appears to be a cat and a rabbit being very friendly, stepping on a scale and weighing 10 kilograms. Then the rabbit gets on with the dog and they weigh 20 kilograms. Okay. Then the cat and the dog get on, they weigh 24 kilograms. And then how much if we put everybody together, in a sense, right? That's the idea. So what we could do here is we don't have to treat this like algebra. However, what would it look like if we did treat it like algebra? Okay, so I'm going to go ahead and get a little bit of white space over here so I can kind of jot some notes down. And let's think about this. So if we were living back in algebra world, we could think of each one of these objects as having a weight that we don't know. And when we don't know something, we can replace that with a variable. So the cat will be C, the rabbit will be R, the dog will be D. Now, this first picture allows me to make a wonderful equation. C plus R equals 10. Okay, now look at the next equation. The next equation, what do I have? I have D plus R equals 20. Got it. Okay, now third equation, come down here. And we see dog plus cat equals 24. Okay, now the goal is what would happen if I have a dog plus a cat plus a rabbit? Okay, now in a traditional class, you might sit here and say, okay, well, hold on, let me see here. Um, okay, so let me take these two equations, and because they are equations, I could add them or subtract them. So what I'm going to do is I'm going to subtract them. I'm going to call them number 1 and number 2. I'm going to say equation 2 minus equation 1. So D minus C, I don't know what that is. I don't know what D minus C is. And then I have R minus R. Okay, well, those go away, right? And then 20 minus 10 would be 10. So I create a new equation that does not have the variable R. This is one of those techniques known as elimination. I get rid of one of my variables. Okay. Then I take equation 3, and I guess this would make equation 4. So now I have equation 3 coming in, and take a look. Look at what I have here. D plus C equals 24. Now that's very interesting because I could once again eliminate by adding, now let me change color here, 4 plus 3, equation 4 plus equation 3, and D plus D is 2D, negative C, or a minus C, because we're subtracting, then you add it back in, those eliminate, giving you 0, and when you add the pieces over here, we get 34. So finally, we get to the end, and we can use the division property of equality, divide by 2, and we get D is equal to 17. What I've just done is I've used some algebraic pieces to find how much the dog weighs. Now I can go back wherever I see D. I know D is actually 17. Now I could go back full algebraic, but I'm just going to go back and say, well, if I know D is 17, 17 plus what gets me to 20? And you could say 3, and now you know the rabbit is 3. You could then come right up here and say, if the rabbit is 3, the cat must be 7, because 7 plus 3 is 10. So that would get you to the end, and you could say, okay, well, now my final answer would be 17 for the dog, 7 for the cat, and 3 for the rabbit. So that's 10. That would be 27 if everything gets on the scale. Okay. This is algebraic in nature. If you're working with elementary school students, though, sometimes you might say, I wonder if that's necessarily the best thing, right? So let's take a look. Are there other ways that we could do this? All right. So here's let me give you two quick ways, and then we'll move on with the rest of this section. I don't want to spend all my time doing just one type of problem. Okay, so let's talk about this. If I was doing this problem, yes, what I could see is I have a rabbit and a cat. I have a dog and a rabbit, and over here I have a dog and a cat. Now, here's one thing you could do if you're working with elementary school students is you simply draw pictures like this, and then you do something and you say, well, what happens if I just combine these top two, right? Now, I'm going to use symbols, but if I was in the classroom, I'd have little cutouts or a little picture of a cat, a dog, and a rabbit. So notice what I would have is I'd have a cat and a rabbit and a dog and a rabbit. And now they're all on one scale. And together that is, you guessed it, 30 kilograms. Notice what I get for that 30 kilograms. I get a cat, a dog, and two rabbits. Okay. Again, I didn't really use a lot of algebra here, right? All I did is just shoved a couple more things on the scale. And then come down to this picture down here. A cat and a dog, isn't that worth 24? So when I see a cat and a dog, I could really just say, hey, that's 24. And you could say, well, let me just rewrite this then. And with the kids, you could say, well, let's take the 24 off and see what remains. And we end up with 6 over here. And on the left side, we have 2 rabbits. Hold on, my pointer just froze. Oh, there we go. Sorry about that. So we have 2 rabbits. So now 2 rabbits is equal to 6 kilograms. Well, we'll just split that in half. Now, again, I would actually have a picture of 2 rabbits. I wrote 2r like it's algebra. With the kids, it would be like r plus r equals 6. And then you could just say, well, I need half of each side. So 1 rabbit is 3. So I've already kind of worked my way into that solution. If a rabbit is 3, then I know a dog must be 17. If a rabbit is 3, then the cat must be 7. 17, 7, and 3, and I get the same answer. It may actually even be quicker. It just doesn't integrate algebra in the traditional sense. Okay, let's try one more approach to this because again, I find these very kind of fun. And when you start thinking about it, you're like, how come my teacher didn't teach me that way? I could have understood it. I don't know. I can't speak for them. All I can do is speak for me. And I'm going to do my best to make sure you learn as many techniques as possible. Okay, so now here comes a fun one, right? So if you're showing this to elementary school kids, once you see that they can combine things onto the same scale, they love it. They're like, well, let's just put everything on the same scale, right? We'll do it. Just why not? Put them all on there. Okay, so what we would have is we'd have a cat and a rabbit from the first one, then a dog and a rabbit. And then the last one, I'd have a cat and a dog. Okay, so I'll put all those together like this. A cat, a dog, a rabbit, a cat, a rabbit. Got it. Okay, so there's everything on the scale. And then all you do is say, well, just put everything on the scale. So I have 10 plus 20, that's 30 plus 20, that's 54, right? There's 54. And if you look at this, take a look at this. Look at what you have. You have a cat, a dog, and a rabbit. And you have another cat, a dog, and a rabbit. And together, they all get you to 54. What are you trying to find here? Actually, this problem, you don't care how much each individual animal weighs. You're trying to find how much all 3 of them together weigh. So if you're looking at that picture and maybe you see it, now, you're like, wait a minute, Scott, I have a cat, a dog, and a rabbit. And then I have another cat, a dog, and a rabbit. So really, I have 2 of these groups. 2 of these groups gets me 54. Waka, waka, waka. I just need half of that. And that will get me to what I want. Whoosh, whoosh, make that 27. And there's your solution. It's exactly the same as we got with algebra. It may actually be fun, enjoyable. And you might be like, hey, let me do another one of those. That's not nearly as hard as I thought it was. All right, let's jump in now into the rest of chapter 8. Okay, we're just going to do 8.1 in this video. So the idea here, now again, this goes back every time you see these sections in the book, they will reference things like Common Core state standards. So in grade 4, they should be able to multiply or divide word problems, represent the problems using equations with a letter standing for an unknown quantity. Okay, so we're moving into that. We're moving into the letter. Now, I used a C and a D. If you were in an algebra class, maybe your teacher said you've got to use an X, a Y, and a Z. Okay, But I love it more when the student is in charge. So you get to be in charge. If you want to be C for cat and D for dog, please do. You do not think you have to use an X and a Y. Notice by the time they get to grade 6, they will need to use variables to represent numbers and write expressions when solving real world or mathematical problems. So algebra and the idea of variables is not going to go away. So what we're looking at as objectives in 8.1 is to translate word phrases into algebraic expressions. We're going to solve equations and word problems, and we're going to find the formulas for the nth term of arithmetic and geometric sequences. This should be a bit of review from chapter 1 and 2 in this Math 105 class. Okay. All right. So big pieces, new terms. In algebra and in arithmetic and really mathematics, I guess I should say, we have the concept of what is known as a constant. A constant is a value. It never changes. Okay. Now we have a concept in algebraic thinking is the idea of a variable. A variable stands for a missing idea, a missing value typically. Although later you'll see it could be a set that could be missing. It could be other object, but we tend to think of that as something that varies. Okay. So when we represent something with an X, this is kind of the fancy X that you'll see, but most of you will probably write it like this. We do have to be a little cautious because that looks a whole lot like multiplication. Okay, so if you're writing X's and you are mixing between multiplication and X, the variable, please try to make a change now and make an X a script X or something like that that will be distinctly different from multiplication. And as you can tell, that's also kind of why we tend to use the dot for multiplication more as we go further in mathematics. Okay. Now, of course, the dot has its own problems. If you write it quickly and too quickly, sometimes the dot isn't right in the middle, which makes it look more like a decimal point. Okay. All right, so keep that in mind. Let's see here. Then we have what's known as an algebraic equation and an algebraic expression. And either of these, what it is it's a combination of constants and variables. So something like this, 3x plus 5, is what we would refer to as an algebraic expression. Okay. If you want to get really fancy, you can say, hey, addition and subtraction break up different pieces. Those pieces, what we used to say in Math 105, these would have been addends, right? But because now we have algebraic components, we call them terms. So this is a two-term expression. And two terms means it has different kind of names or objects. And in Latin, name is nom. Nom, N-O-M. So what we have is instead of one nom, we have two. So we would call this a binomial. This is basically saying there are two terms. And it has words that help you kind of say, oh, a binomial, two terms. Okay. A term is something separated by addition or subtraction. Now we could take that same expression, 3x plus 5 equals, whatever I want to say, 8. And now, because I have included the equal sign right here, we don't call this an expression anymore. The left-hand side would be an expression, and the right-hand side would be an expression. And when we say those two expressions have the same value, we use an equal sign. And that makes this an equation. And an equation indicates that one quantity is equal to another. It also creates a statement. And you remember from Math 105, a statement is something that's either true or false. For example, if someone said 3 plus 5 equals 7, this is a statement. The statement type is an equation, and the statement would be false. When we say 3x plus 5 equals 8, once again, it is a statement. However, it is either true or false depending on the value of x. So x can change. Another way to say change is we could say it could vary, meaning you could put in different values for x and get different truth values for the statement. If you plugged in the number 1, let's try it, right? 3 times 1 would be 3, plus 5 is 8. That would be true. But if you plug in the number 2, 2 times 3, that's 6, plus 5 is 11. That would be false. So we have to know whether this equation is true or false. And we'll see, as you probably have some experience with, a teacher might ask you to solve an equation. The idea of solving the equation is finding the solution. So it's kind of, those mean the same things. All right, so you'll see equations often written with pictures, especially at, what year is this? This is Pearson Student Edition Digital. It doesn't say. Topic 6, Lesson 6.3. So this one is using images. I would estimate this would probably be around somewhere between 4th and 6th grade. The quantities used are not huge. The numbers that are using are linking to subtraction and division. So that's kind of where I would be placing this, even though it doesn't say down here. Well, there it is, grade 4. There it is, grade 4. Phew, read right past it. So grade 4. Again, if you take a look, though, all they're doing is representing the words and turning it into a picture, the picture that might help you create an equation that you could write out and then find the missing piece. Okay. Oh, and I should say back here, this is what's interesting. As you kind of get into these problems, let me zoom in just a little bit. So in this particular problem that was given right here, oops, oh, there we go, right here. What you could see is 98 plus S is equal to 160. Okay. Now, we could use algebra or solving equation tools here. For that, what I'm saying is we could subtract 98 from both sides. This is the property of equality we talked about in Math 105 from chapter 7. Now, when you look at that, that would mean S is equal to 160 minus 98, and then you could solve and get S is equal to 62. Okay. But the other approach to this is to take a look and say, wait a minute, this right here is addition. And I know that subtraction is defined in terms of division, or in this case, in terms of addition. So I could say, so S is equal to 160 minus 98, because the definition of subtraction says, in order to check it, this is true if and only if S plus 98 equals 160. So you could use that other definition without having to use necessarily algebra. So that's a good piece to keep in mind as you go forward, that there's a lot of connections between what we do in class, and there's oftentimes more than one path to get to the same answer. Okay, so what we're going to see in this chapter, I guess this section 8.1, is you're going to get a sentence. The goal is to turn that sentence into an expression, and we want to use symbols. Okay, so we want to represent, in this case, the cost of renting a car for any number of days at $40 a day. Well, picture it in your mind, right? If it was $40 and it was only for one day, you'd pay $40. If it was for 2 days, you'd pay $80. If it was for 3 days, you'd pay $120. So when you think about what you're doing, you are taking the $40 per day as the daily rate, and you're multiplying by how many days are you renting the car. So we don't know how many days. We could say, well, let's call N the number of days, or you could say D for the number of days, D for days. Either one, doesn't matter. You're in charge. And then come up and say, okay, well, my cost is 40 times the number of days. Now, what's missing here is the unit. And so this would actually be measured in dollars. Now, again, you're going to hear me say this a lot. What is your unit? It's also kind of a way of saying, what are you measuring? I'm measuring dollars here. Because if I write 40 times D just by itself, you can't tell whether I'm talking about, maybe this is total number of days. Maybe this is, maybe it's dollars. Maybe it's something else. Maybe it's pickleball. thinking of other things that it could be. Maybe it's depth, right? Um, so, I mean, you have to at least make sure you're clear and say, what are your units? So when you are doing these problems that are listed in the book, make sure here the distance. If I'm measuring distance, I want to make sure that it includes a measurement of distance. So here, when they write it down and say 65 miles, they are communicating not just an expression that represents the number, but they're also communicating what are we measuring. Okay. So a couple of questions like that you're going to see as we go forward. Let's see here. Then you get a little bit of, these are kind of fun ones, where they do kind of what is known as algebraic manipulation. And so here comes the fun. If you take any number, and you can try this. I don't want to scroll all the way down. We'll just take any number, call it n, add 15 to it. Now you can imagine yourself, you're going to, oh my gosh, kids love these things. You're like, what? And you're going to say all these things. And then at the end, you're going to name their number like that. Okay. Now you may be able to see a pattern. So I'm going to do this. I'm going to actually get a number and we're going to follow through with this. Pick any number. Okay. I'm going to pick the number, a 5. Okay, 5. Okay, add 15 to it. Got it. Okay, that's 20, right? You can see all the kids in your class are doing it, right? Multiply that sum by 4. Give them a calculator. It's fine if they need it. Okay, by 4. Okay, got it. 80. Subtract 8. Okay, subtract 8. Got it. 72, right? Divide the difference by 4. Divide the difference by 4. Okay, so 4 goes into 72, right? 4 goes in here. 1, 4. Subtract. Multiply. Divide. Bring down. Okay, 18. Got it. Okay, then subtract 12 from the quotient. Subtract 12. Okay, so 6. Tell me the answer. Okay, so I would tell the teacher 6, and the teacher would be able to tell me my number in a heartbeat. Like, wow. Oh, it's so cool. All right, I know. That's kind of fun. Okay, well, let's try it again. Let's try the different number. Let's try the number 2. Okay, 2, I add 15 to it. That's 17. Multiply by 4, that's 68. Subtract 8 gives me 60. Divide by 4 is 15. Subtract 12 gives me 3. And the teacher should be able to tell me my number in a heartbeat, right? Are you seeing it yet? Are you? Some of you are like, oh, I see it. Let's try one more, shall we? Let's be sneaky. Let's try 0. Add 15, multiply by 4, subtract 8, divide by 4. 58 divided by 4 is 13 because there's 13 cards in each suit in a deck of cards. And then subtract 12 and I get 1. Do you notice any relationship between the student's number and their final answer? Because if you do, you could be shouting out the student's number and showing off your math wizardry. They are going to think you are magical. You will be a mathemagician, we'll say. Okay. But as it turns out, when you do all of those things in general, we could actually show that what you just saw holds true all the time. We get an expression that looks like this: n plus 15 minus 8, the whole thing divided by 4, and then when I'm done, I divide by 12. Why is this so cool? Because the power of algebra allows us to simplify this expression. Okay, so let's take a look. If we're going to simplify this expression, we could distribute the 4 across. Okay, so I now have 4n plus 60 minus 8, the whole thing over 4. Then when I'm done, I'm minus 12. Then I could simplify the 60 and the 8, so I get 4 times n plus 52, the whole thing divided by 4 minus 12. I'm going to use that fundamental law of fractions, floffing. F-L-O-F. So I'm going to pull out a common factor on top. That's 4 times n plus 13. And that whole thing is divided by 4. Then I subtract 12. And take a look here. You see it? I know you do. The 4s go away because they are floffed, baby. And when you get done floffing, you get n plus 13 minus 12. And 13 minus 12 is simply 1. So what does this say? If you take any number and we call it n, and you do all that work, at the end of the day, guess what? You're going to end up with n plus 1. So if you tell me the number 8, I know your original number was 7. And that is the power of algebra. The goal in algebra is to make things simpler. Okay. Now, what we're going to see here is a generalization of arithmetic sequences that we've done in the past. As soon as the page loads, it is like really raining right now. So maybe that's why my internet connection is slow. Okay, there we go. Okay. And what you'll see is generalizing what we've done in the past comes up with the nth term equal to the first term plus n minus 1 common differences. Again, if you took the 105 class last term, you remember this. So the nth term in a sequence is the first term plus n minus 1 common differences. This becomes an algebraic formula. It also becomes a great way of demonstrating that any arithmetic sequence can be written in this way. So if you had a sequence that went 3, 7, 11, 15, dot, 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 you could say, wait a minute, that common difference is 4. My first term is 3. And you could come over here and say, okay, everyone, if your first term is 3, and you could create an equation where someone could put in whatever term number they want, first, second, third, 10th, 100th, and you could find what term that is very, very quickly instead of having to add 4 every time. So if someone wanted the 101st term, you could just say, oh, got it. I do 101 right here, and I'm going to change that to blue so it's very clear what I'm doing. I'm putting 101 where I used to have an N. Where I used to have an N, I put 101. After that, everything stays the same. 101 minus 1, that's 100 times 4 is 400. So my final answer is 403. If you were doing it the long way, you are still adding 4 and adding 4 to get there. The goal of math is to make things easier. We look for patterns, we look for structure, we make things easier. If you encounter a problem that says something like this, the second term is 11, the fifth term is 23, find the 100th term. Hey, that's fantastic. It seems complicated. And the way that they have done it here is algebraically complicated. But you're going to be elementary school teachers. So I want to show you, even though this is in the book and you're welcome to take a look at it, I do not think anything is wrong with this solution, but I'd like to show you another way. And I think some of you have appreciated some of these because they are quite a bit more time consuming. What I know is my second term is 11. I know my fifth term is 23, right? Okay, so if you're picturing this, could I create a formula that says A1 plus 1 common difference because it's 2, and this is A1 plus 4 common differences? The answer is yes. Of course you could. You could absolutely do that. You now have 2 equations and 2 variables, and you can go solve that the way you might have learned in an algebra course. But if you haven't taken an algebra course in a while, it becomes more complicated. All of those techniques, not that they're bad, but the idea of subtracting 2 equations to use the elimination property may not be right at your fingertips. So let's take a look at this. I want you instead to think about this with me as if we were just living in a world where we knew the second and the fifth terms. Okay, so picture this in a sequence. As you move between terms, we know that we add the common difference. So to get from the first to the second, you add a common difference. To get from the second to the third, you add a common difference. Okay. To get from the second to the fifth, I want you to count along with me. If we were living here on the second and we're trying to get over to the fifth, right? Here's the second, here's the fifth. How many steps do we need to take? 1, 2, 3. That's right. So to get to the fifth term, I need to add 3 common differences. So I could just take these and say 23 is 11 plus 3 of those differences. See what I've done? I've created a new equation where I don't even care what the first term is, right? It doesn't matter what the first term is. They just want me to find the 100th term. So do I need this? I don't know if I do. Okay. So now as I go through this, what I could do is use those properties of algebra. And I could say, aha, the difference here is 12. So 12 is 3 common differences, which is like 3 hops. How many hops? 3 hops is 12. This, my friends, is back to division. So you could find 1 hop must be 4 units. Okay, I now know my common difference. And now you could pick either one of these that you wanted to. It doesn't matter. I know if I knew the first term, which you could find pretty quickly once you know the common difference, right? Just step back. Just step back and you're good to go. And then you can use the entire formula. Of course, that reminds me, you'd have to memorize the formula, right? And I know some of you are great at memorizing formulas, and others of you are like, I won't remember it. Perfect. I don't remember it either. I always have to go back and rethink, where does it come from? But if I was sitting here, I could say, wait, if it took me 3 common differences to get up to the 5th term, which it did, right? How many would it take me to get up to the 100th term, right? And you'd say, oh, to get to the 100th term, well, that'd be 98. Perfect. So you could say the 100th term is really just 11 plus 98 common differences. Now, for those of you who are like, Scott, I love the formula. I love looking in the book. I bought a copy of the answer book so that I have all the answers here, and they don't do it the way you do it. I know. They are going to do it by saying it's equal to A1 plus N minus 1 common differences. And then they're going to say A1, they would have to come back up and go backwards to find 7. Okay. And then they would say 7 plus 100 minus 1. That's 99 common differences. Okay. Take a look. Take a look here. See, I have 11. They have 7. So immediately some people are like, aha, it's not going to be the same. Well, wait a minute. 11 is just 7 plus 4, right? And over here, they have 99 fours, and I had 98 fours. But really, I had one other 4. I just put it with the 7 to make the 11, so I didn't have to do an extra step. So you could break it up if you wanted to. Take this 4, bring it over here, and say 99 of them, and then you are right back, and I guarantee you we're going to get to the exact same number. And fun fact, if you really wanted to, you could have started with 23. You could have said 23. Well, I just need to go 95 more steps, right? And that's how I would get there. I don't know. It's like math is awesome. A lot of different ways you can solve these problems. I will leave them up to you. If you think you found a different way and you want to check it, please let me know. All right, generalizations for geometric. This is very similar. It's just now we're using exponents. So here it is right here. AN, right here, AN is equal to AN is equal to A1, the first term, times the ratio to the n minus 1 power. That is area geometric because we're multiplying with a ratio. Remember, the arithmetic is A1 plus n minus 1 times D. All right. Those are the 2 formulas. This is how algebra links to what we've done before. You're welcome to use those pieces as you attempt the homework. Now, if you choose to, you could go in a little bit to the Fibonacci sequence, which is kind of a cool sequence. I'm not going to go too deep into this one. Not that it's bad. As a matter of fact, there's some amazing properties of the Fibonacci sequence, and maybe I'll do something with that. But honestly, I'm trying to focus on the key core pieces. Sometimes, unfortunately, I have to leave the fun for later. Okay. There we go. Okay, so algebraic thinking. This is another one. This is almost like that one from the dog, the cat, the rabbit, right? So it says, this one says, what is the cost of each object? Aha, the cost of each object. Well, as you look, again, you could start looking and saying things to yourself that are algebraic in nature, just because they're not necessarily algebra. So like, look at this from was it like a cantaloupe? Looks like a cantaloupe and a flower and a watermelon. So to get from here to here, right? you could see the cost went up by $1. So each person bought the same vase. So you could say, oh, okay, so I know the cantaloupe, the melon costs $1 more than a cantaloupe because that's what it does, right? So if I took $1 off of this one, $6, that'd be enough to buy two cantaloupes because again, the watermelon's $1 more than the cantaloupe. Ah, okay. So then you could say if that's two cantaloupes, then that must be three. If that's three, this is five. If that's five, then this must be four. And there's your answers. Didn't use a single algebraic equation, but I didn't have to do it that way. I think they do the combination one. Yeah, they do like the, hey, let's shove more stuff together and see what happens. And then once again, you could say, here's $17 by pushing these two purchases together, but a cantaloupe and a watermelon is $7. Whoop, whoop. There it is. And when I say whoop, whoop, let me shade that a little bit so it's clear. Whoop, whoop, right here. This is $7. So take the $7 away from the 17. And then you got just $10, and $10 covers these two vases, which means each vase is $5. Once you know the vase is $5 plus something gives you 8, and $5 plus something gives you 9. And all of a sudden you become this champion of algebra. And I know if only they would have showed you this, maybe algebra could have made a little bit more sense. All right. Well, anyway, that's it for this video. Hopefully 8.1 makes a lot of sense and hopefully you have a lot of fun. I look forward to it this term. All right. Off you go.